Okay, guys, let's just start off. I just want to correct a typo. So I was trying to rewrite this dot product. So what I should have written is delta A2 dotted into E1 is the mod of A2 times the mod of E1 times by the cosine of the angle between them. I think you all know that formula. Good. So look what's happened. We said that we've now got a negative source because this is a minus, everything else is positive for the 3 charge. So the 3 charge, we said we're going to draw in red. So sitting right here, as a result of this fluctuation, we've got a minus, and this is for the 3 field. So now we will have electric field lines of the 3 field coming into here because it's a negative charge. So that's where field lines end. Good. But now we've got the 3 field that can interact with the A field, with the A2 field. So now we're going to look at, so let me just write it here so that you get the logic interaction of A2, delta A2 with uh, the E3. And let's see what this gives. And again, the term that we have to look at, the term we have to pay attention to, is this nonlinear term. So let's rescue that here. Good, here it is. Great. Okay, so now let's start. So this will be equal to, we'll again have an E, we'll have an epsilon A, then we need to sum over the gauge potential. Well, the only gauge potential that's non-zero is delta A2. So we'll have an epsilon A2. And then we have got the electric field. So this is dotted into E. And now we're looking at the interaction with E3. So this will be an epsilon A23. And what you can see is the indices have to all be different for the epsilon to be non-zero. So we'll get a delta A1. So now we're back to producing a 1 field, the same as the charge that we initially set down. We've got the coupling sitting there, and we'll have an epsilon 1, 2, 3. But epsilon 1, 2, 3 is positive. And then we will have a mod of delta of A2 times by a mod of the E3, and we will have a cosine of an angle. Let's maybe call it phi. What is phi? Phi is the angle between A2 and E3. And this expression, whether it's positive or negative, it depends on the angle phi. And the angle phi is, so just so that we don't forget this, it is the angle between delta A2 and E3. So that's the angle that we've got to look at. Okay, so now let's take a look. Over here, at the bottom here, in this region over here, well, the angle between A2 and E3, the blue and the red lines, is naught. The cosine of naught is plus 1. So it's like we've got a positive source of charge. So it's like sitting here, we've got a plus 1 charge. Okay? And in this region over here, now you can see that the direction between the blue arrow and the red arrow are exactly opposite. So there's 180 degrees difference between them. So we've got a minus sign sitting over there. So what does it look like? We found with this plus and the minus, we've again got a dipole, and we've got a dipole, we've got a 1 dipole. This is of the A is equal to 1 type of field. But notice that now in this dipole, the plus charge is closer to the plus charge. The plus charge of the dipole is closer to the plus charge setting up the field, and the minus charge of the dipole is further from the plus charge setting up the field. So now the dipole tends to anti-align with the field. Okay, so let's just make a quick plot. So for screening, if we had a positive sitting here, when we had dipoles, things tended to align like this. The minus went closer to the plus charge, okay? But here you can see, oh, let me just correct that. That diagram is just too terrible. There's the minus with the plus. There is the minus with the plus. Now, in this picture, however, you can see the plus is closer to the plus and the minus of the dipole is further from the plus. So for anti-screening, what did we get? We got a plus, and then the dipoles were aligning like this. So the opposite way to what was happening with the screening. And let's just go through again this calculation. What did we do? We imagine that we put down a +1 charge. Then there was an A2 fluctuation that we considered. With that A2 fluctuation, this acted like a negative E3 field, and that was because of the interaction between the delta A2 and the 1 electric field strength. So we got a negative E3 field, and then the interaction of this negative E3 field with this A2 fluctuation produced the dipole, and the dipole was anti-screening. This is a super important effect, and a lot of the physics of QCD is in here. So remember, what did we say? We said with the screening case, let me just remind you of the argument. We couldn't actually measure point charges anymore. We measured these spheres, and when you added up the charge inside the sphere, there was less charge because we were catching the negatives from the dipole together with the positives of our charge. If we repeat that in the case of anti-screening, you see, now we catch the pluses of the dipoles together with the plus of our charge, it tends to increase the value of the charge. So if we now were to take a look, what is the strength of the coupling E as a function of a P over M or log P over M, so as a function of scale? At high energies, it'll have some value, but as we flow to lower energy, so again, think here we've got our plus charge, and that's the size of the sphere that we can resolve. And then when we go to lower distances, it is a much bigger sphere. That's the length that we can resolve. We land up adding up the positives from a lot more of the dipoles which are excited out of the vacuum. So as we go to low energy, so the coupling starts to increase like that, okay? So the fact that the coupling is very small at high energies, this is called asymptotic freedom. This is a property that QCD enjoys, and it won a Nobel Prize for David Gross, for Politzer, and for Wilczek. And this is a lot of the physics of QCD. And the fact that this coupling becomes very strong at low energies, this we think is part of the mechanism by which confinement is realized. So confinement in QCD is a strong coupling, low energy effect. So what have we discovered? Well, in electromagnetism, we've got screening. In a non-abelian gauge theory, because of these nonlinear interactions, that's what's driven this whole analysis that drew us to the conclusion of anti-screening. It was the nonlinear dynamics of the Yang-Mills field that's led to anti-screening. Screening tends to make couplings irrelevant. They become very small at very large distances. Anti-screening tends to make couplings relevant, makes them grow in the long distance limit. And the way that we're going to get our Banks-Zaks CFT is that we're going to exactly cancel the effect of screening against the effect of anti-screening. How is screening performed? Well, screening is performed by charged matter. And how is anti-screening performed? It's performed by your gauge bosons. So by choosing the right number of gauge bosons and the right number of charged matter particles, we can exactly cancel the effect of the coupling to be screened against the effect of anti-screening. And then we find that the coupling doesn't evolve as we move to long distances. The beta function vanishes, and we've got a conformal field theory. So again, we couple an effect which tends to make the coupling irrelevant against an effect which tends to make the coupling relevant. And that's exactly what we did for the Wilson-Fisher fixed point too.